Welcome to the solution walkthrough for LeetCode problem number 868, titled Binary Gap. In this problem, we'll explore how to determine the longest distance between consecutive ones in the binary representation of a given integer. It's a fascinating challenge that blends binary operations and logical reasoning. Let's dive in. The problem is called binary gap. Here, you are given a positive integer n, and your task is to determine the longest distance between any two consecutive 1s in the binary representation of n. If the binary representation contains fewer than two 1s, the result should be 0. The distance between two 1s is defined as the number of positions between their indices. For instance, if the binary representation of a number is 1001, the two 1s are 3 positions apart, so the distance is 3. The input will be a single integer n, where n is guaranteed to be between 1 and 10⁻⁹. The output will be a single integer representing this maximum distance. Let's dive into some examples to better understand how this works. In the first example, the input is n equals 22. The binary representation of 22 is 10110. Here, the 1s appear at indices 0, 2, and 4, when counting from right to left. To calculate the distances between consecutive 1s, we find the difference between these indices. The distance between index 0 and 2 is 2, and the distance between index 2 and 4 is also 2. The maximum distance between any two consecutive 1s in this case is 2. Therefore, the output is 2. Now, let's look at the second example where n equals 5. The binary representation of 5 is 101. In this case, the 1s are located at indices 0 and 2. Since there are only two 1s, there's just one distance to calculate. The distance between index 0 and 2 is 2. As this is the only distance, the maximum distance is also 2. So, for this input, the output is 2. In the third example, the input is n equals 6. The binary representation of 6 is 110. Here, the 1s are located at indices 0 and 1. The distance between these indices is 1. Since there are no other pairs of 1s, the maximum distance is simply 1. Therefore, the output for this input is 1. Finally, let's discuss the constraints and some edge cases. The value of n will always be between 1 and 10⁻⁹, and its binary representation will always include at least one 1. The distance is measured as the number of positions between indices of consecutive 1s, as we've seen in the examples. If there are fewer than two 1s, the output will always be 0. For example, if n equals 1, its binary representation is 1, so the output is 0. Similarly, for n equals 1024, the binary representation is 1000000000000, which also contains only one 1, so the output is 0. On the other hand, for n equals 15, the binary representation is 1111. Here, the distances between consecutive 1s are all 1, so the maximum distance is also 1. These examples help clarify how the solution works across different scenarios. To solve the binary gap problem, we aim to determine the maximum distance between consecutive 1s in the binary representation of a given positive integer n. Let's start by considering the brute force approach. The intuition behind this method is to first convert the integer n into its binary representation and identify all the indices where the character is 1. Once we have these indices, we calculate the differences between each consecutive pair of indices to find the largest gap. The steps are straightforward: convert n to a binary string, traverse the string to collect the indices of all 1s, compute the pairwise differences, and finally return the maximum difference. If there are fewer than two 1s, the result is simply 0. While this approach is conceptually simple, its complexity involves a time cost proportional to the number of bits in n and a space cost proportional to the number of 1s in the binary string, as we need to store all their indices before performing the calculations. However, the brute force approach has notable drawbacks. It requires additional memory to store the indices of all 1s, which can become inefficient for integers with many 1s in their binary representation. Additionally, the method involves multiple traversals of the binary string, one to identify the indices and another to compute the differences between them, leading to some redundancy. To address these inefficiencies, we turn to an optimized iterative approach. This method avoids storing all the indices by dynamically calculating the gap as we traverse the binary string. Instead of collecting all the 1 positions, we track only the previous index of a 1. Whenever a new one is encountered, we compute the distance to the previous one on the fly and update the maximum gap if necessary. This eliminates the need for extra storage and redundant computations. With a single traversal of the binary string, the optimized approach achieves the same result with a time complexity of O(k) and a constant space complexity of O(1). The optimized iterative approach offers several advantages. First, it requires only a single traversal of the binary string, making it more efficient in terms of time. Second, it minimizes space usage since we no longer need to store an entire list of indices, just a few variables to track the current and previous positions are sufficient. These features make the method particularly suitable for handling large integers, where the length of the binary representation can grow significantly. Given these benefits, this approach was selected as the final solution. The real insight here was recognizing that it's unnecessary to know all the positions of one S at once. Tracking just the previous position is enough to dynamically calculate the distances. This realization significantly reduces both the time and space overhead, resulting in a more elegant and scalable solution. When comparing the two approaches, the trade-offs become clear. The brute force method is more intuitive and straightforward to implement, but it suffers from higher space requirements and involves redundant computations due to multiple traversals of the binary string. On the other hand, the optimized iterative approach is more efficient, both in terms of space and time, without compromising readability. While the brute force approach may be easier to understand initially, the optimized method strikes a better balance between clarity and performance. By eliminating unnecessary storage and computations, it becomes the more practical choice, especially for larger inputs. Ultimately, the chosen strategy demonstrates how careful consideration of efficiency and simplicity can lead to an ideal solution for the binary gap problem. The problem we're tackling here is called the binary gap. Essentially, we need to determine the longest distance between two consecutive ones in the binary representation of a positive integer n. This distance is calculated as the number of positions between their indices. To solve this efficiently, the first step is to convert the number into its binary form. In Python, we can use the built-in bin function, which gives us a string representation starting with 0 be followed by the binary digits. For example, calling bin 22 returns 0b10110. From this result, we can extract just the binary digits by slicing off the first two characters, leaving us with 10,110. This binary conversion sets the foundation for analyzing the positions of ones in the next steps. Once we have the binary representation of the number, we can begin analyzing it. To do this, we initialize two variables, last_position and max_gap. The variable last_position keeps track of the index where we last encountered a 1, starting at -1 to indicate that number 1 has been seen yet. The max_gap variable is used to store the largest gap between any two consecutive ones as we progress through the binary string, and it starts at 0. Using a loop, we traverse each digit in the binary string. If the digit is 1, we check if last_position is not -1, meaning we've seen another one before. If it is true, we calculate the gap by subtracting last_position from the current index. If the gap is larger than the current max_gap, we update max_gap. Finally, we update last_position to the current index of this one. At the end of the loop, max_gap contains the largest distance between consecutive ones, which we return as the result. To solve this problem, we rely on a few simple data structures. The variable last_position helps us track the index of the most recent one, while max_gap keeps track of the largest gap found so far. Both are initialized efficiently, with last_position set to -1 and max_gap set to 0. The binary representation itself is stored as a simple string, which is sufficient for our needs and keeps the solution memory efficient. Now, some key insights make this approach particularly effective. First, converting the number to its binary form simplifies the task of identifying and comparing the indices of ones. Second, by iterating through the binary string in just one pass, the algorithm achieves a time complexity of O(k), where k is the length of the binary representation. Lastly, it's critical to handle edge cases, such as when there are fewer than 2 ones in the binary string. For example, if n equals 1 or 2, there's no gap to compute, so the result should be 0. Even for very large numbers with sparse ones, this approach remains efficient due to its single traversal. To understand how the algorithm works in practice, let's go through an example with n equal to 22. First, we convert 22 to its binary form, which gives us 10,110. Next, we initialize our variables. Last underscore position is set to -1, and max underscore gap is set to 0. Now, we start iterating through the binary digits. At index 0, we encounter a 1, so we update last underscore position to 0. At index 1, the digit is 0, so we skip it. At index 2, we find another 1. The gap between this index and the last underscore position, which is 0, is 2. We update max underscore gap to 2 and then update last underscore position to 2. At index 3, we see yet another 1. The gap between this index and last underscore position is 1, which doesn't exceed our max underscore gap, so max underscore gap remains 2. We update last underscore position to 3. Finally, at index 4, the digit is 0, so we skip it. After completing the iteration, we return max underscore gap, which is 2, as our result. This algorithm can be further optimized in a few ways. For instance, we could implement an early exit condition. If we encounter the maximum possible gap, such as in a number like 2 to the power of k1 where all binary digits are 1, we can terminate the loop early since no larger gap is possible. Another optimization involves replacing the string approach with bitwise operations. Advanced users can use bitwise shifts and masking to analyze the binary digits directly, avoiding the need to convert the number into a string entirely. In terms of complexity, the algorithm is already efficient. The time complexity is O(k), where k is the number of bits in the binary representation of n, and the space complexity is O(k), due to the binary string. If we use bitwise operations, the space complexity can be reduced to O(1). These features make the solution both fast and memory efficient, even for large inputs. This solution efficiently solves the binary gap problem by leveraging Python's built-in bin function to convert the given integer n into its binary representation. The binary representation is stored as a string, stripped of the 0b prefix. Next, two variables are initialized, max underscore gap, which tracks the maximum distance between consecutive ones, and last underscore position, which tracks the index of the most recent one encountered during iteration. Initially, last underscore position is set to none to signify that no one has been found yet. The solution iterates through the binary string using Python's enumerate function. The enumerate function provides the index, I, and the corresponding bit, at each step. If the bit is 1, the algorithm checks if last underscore position is none. If not, it calculates the gap between the current index and last underscore position, i.e., last underscore position, and updates max underscore gap if this gap is larger than the current max underscore gap. Finally, last underscore position is updated to the current index. After completing the iteration, the value of max underscore gap is returned as the result. This approach ensures that the algorithm efficiently computes the maximum binary gap in n time, where n is the length of the binary representation of n. The code handles edge cases, such as inputs like 1, binary 1, where no gap exists, by returning 0. The algorithm is efficient and concise while maintaining clarity and correctness. This is the Java implementation of the binary gap problem. The logic mirrors the given Python solution, with key differences such as type declarations, the use of Java's integer.to-binary string method for binary conversion, and the absence of Python-specific constructs like enumerate. The code iterates through the binary string representation of the number, calculating the maximum distance between consecutive 1 bits. To solve this problem, we start by converting the given integer n into its binary representation. For the input n equals 22, the binary form is 10110. We remove the 0b prefix so that the binary representation becomes a simple string, 10110. Next, we initialize two variables, max underscore gap to 0, which will keep track of the largest gap found, and last underscore position to none, which will store the position of the last one we encountered. Now, we iterate through each bit of the binary string. At index 0, the bit is 1. Since last underscore position is currently none, we set last underscore position to 0. At index 1, the bit is 0, so we skip it and move on. At index 2, the bit is 1. Here, we calculate the gap as the difference between the current index 2 and last underscore position, which is 0. This gives a gap of 2. We update max underscore gap to the maximum of its current value, 0, and this gap, resulting in max underscore gap equals 2. We also update last underscore position to 2. At index 3, the bit is 1 again. The gap between the current index 3 and last underscore position, which is now 2, is 1. Max underscore gap remains 2 since 2 is greater than 1. We then update last underscore position to 3. Finally, at index 4, the bit is 0, so we skip it. After completing the iteration, we return the value of max underscore gap, which is 2. Now, for the input n equals 8, the binary representation is 1000, and we strip the 0b prefix to get binary underscore representation equals 1000. As before, we initialize max underscore gap equals 0 and last underscore position equals none. Iterating through the binary string, at index 0, the bit is 1. Since last underscore position is none, we set last underscore position to 0. At index 1, the bit is 0, so we do nothing and continue. The same happens at indices 2 and 3, where the bits are also 0. Since there is only one 1 in this binary representation, no gap can be calculated. With no updates to max underscore gap, it remains 0. Thus, we return the result max underscore gap equals 0. For the input n equals 5, the binary representation is 101. Removing the 0b prefix, we get binary underscore representation equals 101. As before, we initialize max underscore gap equals 0 and last underscore position equals none. We now iterate through the binary string. At index 0, the bit is 1. Since last underscore position is none, we set last underscore position to 0. At index 1, the bit is 0, so we do nothing and move forward. At index 2, the bit is 1. Here, we calculate the gap between the current index 2 and last underscore position, which is 0. The gap is 2, 0 equals 2. We update max underscore gap to the maximum of its current value, 0, and this gap, resulting in max underscore gap equals 2. We then update last underscore position to 2. After completing the iteration, the largest gap we found is 2, so we return max underscore gap equals 2. To analyze the time complexity of the binary gap function, we need to break it down into its main components. First, the operation bin en 2 converts the integer n into its binary representation, excluding the 0b prefix. The time it takes to perform this conversion depends on the number of bits in the binary representation of n. Since the number of bits is proportional to log underscore 2, n, the time complexity of this step is O log n. Next, we have the for loop, which iterates through the binary string. The length of this string is also proportional to log n, and within each iteration, we perform constant time operations like checking the value of each bit and updating variables. Therefore, the cost of the loop is linear with respect to the length of the binary string, which is again O log n. Combining these two dominant steps, the total time complexity of the function is O log n. Now, let's discuss the space complexity of the binary gap function. The main contributor to space usage is the binary underscore representation string, which stores the binary form of n. Since the binary representation has at most log underscore 2, n, plus 1 bits, this requires O log n space. Additionally, the function uses two auxiliary variables, max underscore gap and last underscore position, which are simple integers and therefore require constant space, or O1. Importantly, no additional data structures are created in this function. As a result, the space usage is dominated by the binary string, leading to an overall space complexity of O log n. Let's compare this optimized approach with a brute force method. A naive solution might iterate through all integers from 1 to n, compute the binary representation of each, and find the maximum gap for every number. This would involve O n asterisk log n time, where log en, accounts for the binary conversion of each number, and n represents the total numbers iterated. The space complexity in that case would still be O log en, due to storing the binary representation for each number, but the time complexity is significantly worse. In contrast, the optimized approach we're using focuses only on the binary gap of a single number n, avoiding unnecessary overhead. It achieves a time complexity of O log n and a space complexity of O log n. Additionally, whether we consider best, average, or worst-case scenarios, the optimized solution consistently processes at most log n bits and maintains the same time complexity of O log n. This makes it far more efficient than the brute force alternative. Finally, let's solidify our understanding of the time complexity with a mathematical proof of the O log n bound. The binary representation of any number n has at most log_2 n plus 1 bits. This means any operation that depends on the binary representation, such as conversion or iteration, is inherently limited to O log n. Within the loop, each iteration involves a fixed number of constant time operations like comparisons and updates, so the total cost of the loop is directly proportional to the length of the binary string. When we combine all the operations in the function, including both the binary conversion and the loop, the overall time complexity remains O log n. Similarly, the space complexity is governed by the storage of the binary string, which also depends on the number of bits in n, leading to an overall space complexity of O log n. This confirms that both the time and space complexities are optimal and tightly bound to the input size. When working on the binary gap problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to incorrect results. For example, if the input number has fewer than 2 1s in its binary representation, such as powers of 2 like 16 or 32, there's no gap to measure. The binary gap is defined as the distance between consecutive 1s, so in cases like these, the correct output should be 0. Forgetting to handle this scenario might cause runtime errors or incorrect answers. Another common error is calculating the distance incorrectly. Remember, the binary gap is the difference between the indices of consecutive 1s, not the count of zeros between them. Misinterpreting this can result in subtle off-by-1 errors. Finally, failing to consider edge cases during binary conversion can lead to performance issues. For instance, when dealing with large values of n, like 10⁻⁶, inefficient conversion or traversal methods can significantly slow down your solution. It's important to account for these potential pitfalls to ensure your code runs correctly and efficiently. Additionally, using strings inefficiently is a frequent mistake to avoid. While it's tempting to convert the binary representation into a string and then use slicing or splitting operations, these approaches can significantly increase the time complexity, especially for large numbers. Such inefficiencies can make your solution impractical for larger inputs. Another issue arises from misunderstanding the problem constraints. Some developers overcomplicate their solutions by attempting to handle negative numbers or non-integer inputs, even though the problem explicitly states that n is a positive integer. Spending time on these unnecessary cases not only wastes effort but can also obscure the simplicity of the solution. Staying focused on the problem's actual requirements will help you write cleaner and more efficient code. To approach this problem effectively, it's helpful to keep some key interview insights in mind. First, be comfortable with converting integers to their binary representations, whether you're using bin, n, in Python or integer dot to binary string, n, in Java. Efficiently iterating through the binary digits is crucial. This problem can also be thought of in terms of a sliding window or two-pointer approach, where the objective is to identify gaps between elements of interest, in this case, the 1s in the binary representation. Optimization is another important aspect. For instance, you can skip over any trailing zeros in the binary form, as they won't contribute to the gap calculation. It's also essential to clearly explain how your solution handles edge cases, such as when n is 1, binary 1, or a power of 2, binary 10, 0. Finally, when presenting your solution, make sure to discuss the trade-offs between space and time complexity, particularly when comparing string-based methods to bitwise operations. This demonstrates your ability to evaluate and choose the most appropriate approach for the problem. Exploring related problems can help deepen your understanding of binary manipulation and its applications. For instance, in LeetCode 191, you count the number of 1s in the binary representation of an integer, which is a foundational skill that's directly applicable to other binary problems. LeetCode 461 focuses on the Hamming distance, where the goal is to determine the number of differing bits between two integers. LeetCode 338 builds on this by asking you to count the number of 1s in the binary representation for all integers up to n, which can be solved using dynamic programming. Lastly, LeetCode 693 challenges you to determine if a number alternates between 1 and 0 in its binary representation. These problems share common themes, such as binary conversion and efficient bitwise operations, making them excellent practice for strengthening the skills needed to solve the binary gap problem. Finally, let's consider some alternative approaches to solving the binary gap problem. A string-based approach involves converting the integer into its binary representation as a string, then iterating through it to find the indices of 1s and calculate the gaps. While this method is straightforward and easy to implement, it's less efficient due to the overhead of string operations. A more efficient option is the bitwise approach, which uses bitwise operations to directly identify the positions of 1s without converting to a string. This method tracks the previous index of a1 and updates the maximum gap as it processes the number. While faster, it requires a solid understanding of bitwise operators and might be less intuitive for some. Lastly, a pre-processing approach involves pre-computing the binary gaps for smaller integers up to 10⁻⁶, for example, and storing them in a lookup table for quick access. This is useful in scenarios with repeated queries but comes with the trade-off of additional pre-processing time and memory usage. Each of these methods has its advantages and limitations, so choose the one that best fits the constraints and context of the problem you're solving. Great job completing the problem. Today, we reviewed how to calculate the longest binary gap, emphasizing binary operations and stepwise problem solving. Remember, understanding bit-level manipulations can strengthen your problem-solving skills for similar challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!